Thank you, Tobias, and good morning, afternoon, and evening, everyone. It's really great to be hosting this webinar on advancing computer vision on the edge with different machine learning approaches. A quick intro about myself. I joined Arm around 1.5 years ago, and I'm part of the IoT line of business here at Arm. And I'm primarily responsible for ensuring that several billion cameras and vision devices that are created in the future are all based on Arm technology. So one of the key things is the image sensor continues to be one of the most important information generating devices. And the demand for computer vision in machine learning in the future devices continues to grow exponentially. So that's the reason we thought that this would be a great panel discussion that we should have on this topic. And this is what we have for you all today. So we'll start with some introduction of the panel themselves. So I'll request each one of them to introduce themselves first, along with brief introduction about their company. After that, I have some key topics that I would like to bring up to the panel for discussion. And after a great discussion, we'll obviously summarize and ask each of the panelists to provide their final thoughts. If you have any Q&A, feel free to type in, as Tobias said, and I'll pick the appropriate time and ask the panelists to answer. So with that, I think let's start with our panel first. So first, we have Nick Romano, co-founder and CEO from Deeplite. So Nick.
Thank you, Parag. It's great to be here today, and thank you so much for having me on the panel. So as I said, I'm Nick Romano. I'm co-founder and CEO of Deeplite. I'm a graduate of McMaster University in Hamilton, Ontario, Canada, engineering and management program. I've been in the tech space since the late 90s, three-time founder, and met my co-founders in 2018, Asan Saburi and Davis Sawyer. We created Deeplite and launched it in the summer of 2019. So very excited to be here. If you want to just sort of jump to the next slide, I'll talk a little bit about Deeplite. So Canadian company, we're in Montreal and Toronto, as I mentioned, founded in 2019. Our core thesis is basically what we call AI for everyday life. It's about making deep neural networks smaller, faster, and more energy efficient so that they can be deployed in the things that we use every day. And we do that through a couple of components to our software stack. Deeplite Neutrino is our optimization platform. So this would sit within your own data center, co-located with your training stack and whatnot. You don't have to send us data, you don't have to send us your models. But with the Neutrino platform, there's a lot of different tools that you can use to make your models more efficient. So we've got architecture optimization, where we literally focus on the model architecture itself, using this proprietary concept called design space exploration, where we will literally resolve a new model architecture for you while preserving accuracy. It's a hardware agnostic optimization at full precision, so that you can use whatever toolchain you were using before, just with a more efficient model, again, without compromising that accuracy. We've also introduced quantization-aware training. So we can now quantize models down to 2-bit, 1-bit, actually mixed precision based on what your use case is, all again, designed to preserve accuracy. This is more hardware aware, and this is what's really exciting about our partnership with Arm, because the first hardware platform that we're supporting is Cortex-A CPUs. And then we also, to support the inference of these low precision networks, we created our own runtime engine called Deeplite RT, specifically designed to run this inference on device on these Cortex-A CPUs and shortly Cortex-M as well. And generally speaking, we can get into details if you're curious about metrics, but we're basically much faster than the alternatives from an inference perspective on these devices. We have native PyTorch support, and in some use cases, we're actually approaching GPU type speeds on the CPU. So it's pretty cool stuff that we're doing.
Thank you, Nick. Next in line is Roland, who is also the co-founder and CEO of Plumerai. Roland, up to you.
Yeah, thank you, Parag. Yeah, so I'm Roland, a co-founder CEO of Plumerai. So we started this company about 4.5 years ago, 2017. Our headquarters in London, in the UK, but we also have an office in Amsterdam, in the Netherlands, and an office in Warsaw, in Poland. Could you go to the next slide? Yeah, so I believe there will be hundreds of billions of tiny intelligent sensors. But to get there, I see that you need to overcome two obstacles. So the first one is that you need to deploy powerful, accurate AI on chips that are really cheap, so cheap that it's worth it to embed them in any device. And you need to deploy powerful, accurate AI on chips that are really low power, so that these can be battery powered and that you can just deploy them anywhere. So we're working towards solving those two obstacles. And we're doing that by working on the full AI stack. So all the 4 layers of the embedded AI stack. So the first layer is the data side. So that contains both our training data sets and data pipeline. Second layer of the stack are our model architectures and training strategies. So we both use 1-bit, so those are binary neural networks, and 8-bit model architectures, depending on the platform that we deploy it on. And we've been able to make these model architectures really tiny. So for example, we have a complete solution for people detection and people tracking. And that model is just 1 megabyte large and extremely accurate. Then the third layer of the stack are our inference engines for different platforms, including Arm Cortex-A and Arm Cortex-M. And our inference engine for Arm Cortex-M is actually the fastest in the world. This has been confirmed by the ML Commons ML Perf benchmarking organization, so a third party. It's on average 1.7 times faster than TensorFlow for microcontrollers with ARM SimSysNN, and it's 2 times more memory efficient, more RAM efficient, and all that without any changes to the accuracy. And then the fourth layer of the AI stack that we're working on is our accelerator IP core. That is small enough to even fit on the smallest FPGAs. So yeah, so those are all the 4 layers of the embedded AI stack that we're working on. And to create a good solution, every layer of those, all the 4 layers of that stack need to be excellent. And at the same time, all those layers have to be deeply intertwined with each other. So this means that we can't easily provide a solution for every possible task that a customer might have. But it does mean that what we do provide, and at the moment that is people detection AI or people tracking AI, is by far the most efficient, most accurate solution on the market. So it can detect people from more than 20 meters or 65 feet distances, works in the day, at nighttime, with complex backgrounds, with lots of moving objects, it all works fine. And it can even run on Arm Cortex-M microcontrollers. So I think on this slide, there are a few benchmarks that you can see for Arm Cortex-M and Arm Cortex-A platforms. So it runs very fast with a very small memory footprint. And it's also extremely accurate.
Okay, thank you, Roland. Next, let's move to Deepak, who is also co-founder and CEO of Roviero. With that, Deepak.
Hi, thanks Parag, thanks Tobias, and thanks Arm for having me as part of this panel. I'm really happy to be here and happy to be part of this discussion. This is a really important topic, specifically applied to AI ML when it's applied to the vision. I have been the CEO co-founder for Roviero for more than a little bit over 2 years now. I have more than 24 years of experience in designing semiconductor systems and softwares, and I have experience in running large teams. And right now, Roviero, can you move to the next slide? We'll talk about the company next. Roviero is based out of San Jose. We have offices in Romania and India. We were funded back in 2019, and we are a little bit different from other panelists here. We are a pure IP provider. So what that means is we have a hardware IP that scales in performance from anywhere below, less than 1 TOPS to greater than 500 TOPS. So it applies to various applications. We provide a full software stack that goes with it. And we give full reference applications that go along with it. So be it object detection, person detection, super resolution, or noise reduction on the sensors. We provide all of those as reference applications for our customers. The IP is a fully programmable processor. What that means is that it is completely agnostic to any networks that you can run. So you can run any of the RNNs or traditional DNNs or CNNs on it without any changes to the IP. We have these IPs available running on FPGAs, and our architecture and performance metrics are all displayed on our website. We welcome everybody to visit our website. We're perhaps the only one that demonstrates actual performance on different networks, large and small networks running on our FPGAs. We have some videos available that demonstrate our IP's capabilities, where we demonstrated 5 cameras connected to our systems running only at 62 megahertz on an FPGA doing object detection on the streets, on the cars. ADAS is not the only application, but given that that is a hard application, we have a demonstration we have a demo that shows that. We allow our customers to log into our FPGAs, and there they can run our software stack, run through the FPGAs. They can take their neural networks, take it through the whole application stack and run their whole applications. We even let them modify their FPGAs to put their part of the IP into it. And recently we introduced Core-D1 Premium. What that is where the ARM cores are deeply embedded inside our IP. With that, customers can write their own activation functions. That gives them a very highly programmable and future-proof product. That is a quick introduction of a pretty complex solution that, or very diverse solution that we are providing.
Thank you, Deepak. I know there are a few questions in chat and Q&A. We will get to them after we finish our initial panel discussion. So just hang tight. All right, so this is how we're going to do it. I have a set of questions that I thought through, that I see as part of my daily role. So I'll start with Deeplite first, and specifically maybe go into Deeplite RT, and this should also answer one of the questions that one of the folks asked in the Q&A. So one data point that I wanted to let everyone know is there are about 1 billion, not million, but billion cameras already installed all around the world. And these cameras currently, some of them have ML capability, either as an additional hardware IP, or some of them try to run ML on the CPU. So this question specifically is for Nick from Deeplite. So you've had success in deploying your solution on Cortex-A, Cortex-M. Can you share what sort of end use cases that you're seeing with Deeplite RT? A little bit more detail.
Yeah, I mean, so I wish we were on billions of cameras. We're not quite there yet, but we're just, that's part of the awareness of sharing our story. I mean, the ability now that we're able to take optimized models, quantize them down to these low precisions and run these models using Deeplite RT on this commodity hardware, it's really sort of opening up the realm of possibility for organizations that have, thousands and thousands of legacy cameras in their inventory. I mean, it's all fine and good. A lot of applications talk about new products and what's coming to market, but the ability to actually repurpose existing inventory and existing installations, that's massive ROI for these types of companies. So, quite frankly, these cameras really, historically, if they wanted to have more advanced analytics or AI, they would have to stream video to the cloud and do the analytics there, which can be very, very expensive. while you're processing and streaming that video. What we allow and what we're providing for our customers is the ability to be able to deploy, person, vehicle, pet type detection models into very, very small, into the CPUs that are already embedded on the boards of these cameras. And all of a sudden, we turn what had been a dumb camera into a smart camera, and the ability to perform those analytics right on those devices. And it's not just the ability to deploy or have that AI operating on that camera. It's the tooling that we've built into the process so that you can actually, deploy these models and manage the delivery of these models into literally thousands of cameras. That's part of the secret sauce too, is the engineering to actually, do that in a practical way and maintain and manage that process. So, and cameras is just one example. You talk about billions. There's billions of all kinds of things that have CPUs embedded in them. That we're just waiting for the customer to come up with interesting ideas on what kind of capabilities they want to put on those devices, and we can make that happen.
Great. So since you're already having chat, have you tried running ML models on Cortex M0 or M0 Plus using Deeplite RT?
No, we're Cortex M platform is something we're working on right now. So that will be coming out later this year. Right now, it's still very much Cortex A.
Okay, got it.
Yeah.
Okay. All right. Thank you, Nick. Let's move to Plumerai for the next question. So in general, I think many people think that the public data sets that are available for object detection or any of these use cases are enough, but that's not actually completely accurate. So the question is for Plumerai, how should the ecosystem take the training data set part of ML seriously, and how can Plumerai assist in making it happen?
Yeah. Okay. So I agree. The public data sets that are out there are a really bad proxy for real world performance. So indeed, we've been taking our training data very seriously, and also validation data. So our data set just for people detection consists, our data set consists out of more than 32 million images. So it's really, really large. We go out in the fields every day to collect our own data. And every day we hire so-called data actors to recreate specific scenarios where our models fail or might fail. And it's not just about having a large collection of data, it's also about the quality of this data. Our models are really tiny. So as I mentioned, for people detection, our model is just 1 megabyte large. And we even have models that are smaller than that. So since these models are so tiny, you can imagine that they have limited information capacity. So you have to be very strict in telling these models what they should learn and what they should not learn. And the way to do this is by properly curating your training data sets. And that's what we've been doing. And that's what we've been doing a lot of work on. So we initially looked around to see what data tooling was available on the market that we might be able to use. But none of these solutions, none of these data tooling solutions in the market was powerful enough for us to use it. So that's when we decided to build our own data tooling and data infrastructure from scratch, which allowed us to really tailor it to the needs of tiny AI models, and mostly computer vision models. So our in-house data tooling allows us to figure out where our models require more data, where they require less data, why our models fail in certain cases. We can use it to figure out which data samples should be oversampled, by how much, where in the training process. We have our own auto labeler set up. We have so-called data unit tests to really ensure to our customers that our people detection software works reliable in different settings and with different people. So with data unit tests, for example, for a range of different skin tones, or for people that are only showing their back, for people standing close to the camera or standing at large distance from the camera, for different lighting conditions, etc. Yeah, so I think a lot of the attention in the Edge AI ecosystem is going to the latest silicon, what the latest silicon looks like. And I do think that's important. But what I've seen is that you can get even larger gains by taking your data very seriously. And that's what we've done. And that's often has a bigger impact on the final product. And then, yeah, there are also quite a lot of products that make it really easy for embedded ML developers to build a proof of concept. But from what I've seen, these solutions don't scale well to more complex tasks like people detection. And I strongly believe that to make a production-worthy solution for example, people detection or people tracking, you need a very different approach, our approach.
No, I totally agree, Roland. I think if for folks who are following more on the ML side, there's a professor called Andrew Ng, who's at Stanford, and he also has a company called Landing AI. I think he is also he has a firm belief that companies should spend more on the data side rather than trying to figure out which model to use or stuff like that. So I think I totally agree with your comments. All right, thank you, Roland. Let's move to Deepak now. So you mentioned about, you loaded up your car with FPGAs and decided to find the street lights and people with your IP in the car. Now, let's assume that there is a silicon company who's trying to build ML into their SoC. So can you tell the audience more about how should they think about using your product for their ML solution?
Yeah, absolutely, sure, yes. And I think, like you said, I think in the demo that we did with the camera, right? And I think it really is a demo. And when somebody is designing a silicon, it's a very time-consuming, resource-consuming process, right? I mean, it is not as simple as buying an app off the market. If it works, it doesn't work. Good to go, right? Companies need to sink in millions, hundreds of millions of dollars here, right? I was just looking at the data from one of the analyst forums, and I did not realize this, but it takes $500 million from design verification to all the way tape out on a 5 nanometer chip. Okay, and if a company is really looking to put that kind of money into or resources into designing a system, they're not going to pick something and just go with it, right? So that's where what we have done is we have created a comprehensive solutions for our customers to really create a solution in the software space first, so to say. And that means they can take the models that they want to run, they can create the applications on first of all, on our C models, right? Our C models are 100% bit accurate with the hardware. What accuracy and performance you're going to get from the C models, you're going to get exact same performance and accuracy from the hardware, final hardware. I can imagine it's much easier to do something, a lot less resource consuming. The second step is going on the FPGAs, and we want to work very closely with Arm on the total solutions. The same space there, where the customers can actually design their whole system on the FPGAs. That's what the demo was about, to say, hey, it's working on an FPGA only at 62 megahertz running real applications, right? And there we provide full reference application software stack. We are noticing some of these customers that are showing up are not traditional chip manufacturers, right? Camera module manufacturers and your conference camera manufacturers, they want to make their own chips. And there are multiple reasons for it, right? They're not chip design experts. And how do we go out and give them, these reference applications that are fully running, to give them the comfort of, okay, once I go in this path, it's going to work, right? And we work very closely with them on designing the whole system And once that has happened, right, that's when they go in and start working with us, with their ASIC partners. Some of them are not traditional chip manufacturers, like I said, right? They work with ASIC partners. So we work with their ASIC partners to ultimately put the AI, our AI IP into the ASIC itself. A big part of that is how does it work together in a system, right? Where there are multiple ARM cores running as host or maybe not as host. But so all of this IP, the IP interfaces, if you will, right, from the hardware perspective is also simplified dramatically using pure AXI interfaces, and it really is a drop down, right? We recently integrated our driver software with some of the ARM driver softwares, where with a click of a button, you get the Core T1 driver integrated with the ARM software, right? And from the user perspective, what that means is that they have access to a routine, says call the AI acceleration, and then the result shows up and get the results. So the idea there is to reduce the pain points for our customers who already are sinking in so much resources into it. But that in a nutshell is our goal. It's not just about KPIs and PPAs. They are important, but we believe what's more important is to walk with our customers in giving them confidence that once they design this hardware IP in there, it will work as an end product. And more importantly, once the silicon has been created, it can be programmed more. That's where the Core T1 Premium comes in. It is extremely highly programmable. Customers used to ask us, oh, what functions can your IP really implement? And today our answer has become anything goes. Anything really works, and you can program anything on our IP. It is not limited to any set of functions.
Perfect,
Yep,
perfect. Thanks. Yep.
Maybe we went too long, but wanted to give an overview of what.
I think you're talking from a customer experience point of view, right, which is important. No, perfectly fine. All right, so now let's dig deeper into computer vision side. So we kind of did the intro. So now I'll ask some specific questions by taking specific use cases into mind, and then I'll request each of the panelists to comment on one of the topics. So first is object detection and segmentation. So this is specifically for Nick. So let's take the first use case, that is, object detection segmentation, which is a valid use case for something like smart manufacturing. So for the audience, right, like object detection segmentation is a computer vision technique in which a specific scene is segmented into different frames so that you can detect objects such as people, animals, equipment, etc., etc. So Nick, can you share how Deeplite's product portfolio can help solve this problem, and why would customers come and pick your solution?
Yeah, it's interesting because we're right in the middle of a project where we're doing exactly that, object detection and segmentation. And obviously I can't name the customer who it is, but basically the idea is it's to spot. They've got cameras, they've got basically recorders running on NVIDIA TX2 and Jetson Nanos, depending on what the situation is. So they've got multiple camera streams that they've got installed in hundreds of locations. The use case that they're looking for is there's crowds of people that appear at different times, and they need to detect the people, and then they also we're using segmentation to identify clothing colors. So, for example, spot everybody in the crowd that's wearing a red shirt or something like that. So it's a pretty sophisticated application. They obviously have other things that are running within that infrastructure, but they want to deploy the solution at the edge. So the way they're using Deeplite, it's kind of multi-dimensional. We're helping them with the model development because we've got some expertise, particularly around the data scenarios that they're to make that each location as accurate as possible. But in order to deploy these types of applications, even on this NVIDIA hardware, these are their edge hardware. They've got memory constraints. There's performance requirements. So we're using a combination of Neutrino's optimization capability, the just regular full precision optimization, so that we can fit the applications into the memory constraints of the devices in these scenarios. So we're optimizing for the device for performance and speed, but then we're also using Deeplite RT. Can't get into some of the details, but they're offloading some of the application work that was formerly on the GPU. We're moving it to the CPU, and we're using Deeplite RT to do some of the lighter AI applications on that particular chip. So we're able to optimize the use of, again, their existing deployed infrastructure, so they don't have to upgrade, they don't have to buy new gear. They can leverage what they already have in the field and add a brand new high value feature to their customers. So in the content, and so just going back, it's literally a detection segmentation type application.
Perfect. Thanks a lot, Nick. Let's move to the second problem or second aspect of computer vision. So here, I think, Roland, you mentioned about people detection already in your intro and also your first question. So a couple of things you should know is currently there are like quite a few number of companies who are selling these doorbell cameras that enable individual homeowners to deploy cameras in the front door. Here in my home, pretty much when I walk in my neighborhood, pretty much everyone has either an Arlo or a Ring or something, or even a Nest video doorbell. So this specific question is for Roland at Plumerai. You already touched upon a little bit on people detection. Can you deep dive a little bit more on how Plumerai is helping solve this problem?
Yeah, sure. So we provide customers a complete software solution for people detection and people tracking. And we're deploying this in many different ARM-based platforms. So this solution combines both our data work, our model architectures and training strategies, and our inference engines. So one ARM-based platform they deploy is Arm Cortex-M. So for example, it looks like this. So this is an Arm Cortex-M7 board from STMicroelectronics connected to a really low-cost Omnivision camera. And look, it can do people detection in real time. I mean, here it's quite easy because I'm quite close to the camera, but it even works at 20 meters distances. So there it's running with about 2.5 frames per second. We've also been deploying our people detection on video doorbells. So these things look like this, for example. Typically there's an older ARM Cortex-A core in it, like a Cortex-A7 or Cortex-A5. We've also been deploying it on Cortex-A53 or A72. Yeah, so the Cortex-A core in these video doorbells very often also running other software applications. And then only a small percentage of the CPU cycles is available for our people detection software. But since our models are so tiny and our software is so efficient, we can still make it work, even if there's only like 20 or 30% cycles available, even if there's only if a very old Cortex-A or Cortex-M core is being used, it's not a problem for us. Yeah, so for customers, for most of these customers, they already have their devices in the field, or they have already made their devices, and then it's just a software update, often an over-the-air software update. And it's also important that it's not just detection, but also tracking. So tracking allows you to see if the same person is hanging around in front of your door for a long time. So you can detect like a lurker in front of your door, which is important for these video doorbells. It allows you to detect if someone is approaching the door or walking away. So tracking is also very important, not just people detection. You can detect and track more than 20 people at the same time. Yeah, and so it works well for different image sensors with cameras with a very large field of view, even if it's 180 degrees, that still works fine. Yeah. So we see a lot of traction with video doorbells. For video doorbells, people detection is just extremely important and needs to be very accurate. It's very annoying if your people detection is inaccurate because these customers turn it off immediately because you get lots of false notifications. And running it in the cloud is just very expensive. For many of these devices, it was the only solution. It used to be the only solution because it was impossible for them to make their model small enough to run it on the device. Well, we've been changing that. But lots of these cloud subscriptions cost $3 or more per month per camera, which is expensive. So a lot of these customers are actually not don't have any of these cloud subscriptions because it's just too expensive. And then there are obviously bandwidth limitations. If you have multiple smart cameras in your home installed and they're streaming video all the time, well, bad luck. And there are a few other applications as well where there's a lot of interest. So security cameras, video conferencing cameras, air conditioning systems who want to know where people are standing so that they can direct the airflow, replacing old-fashioned passive infrared motion sensors, making them more intelligent, applications like that.
No, perfect. Thanks a lot, Roland. All right, now let's move to slightly different use case. I'm hoping many people have heard about super resolution. So just to give you a very basic example, super resolution is nothing but upscaling the content that you receive. If you have an 8K TV, but the content is say 1080p or 4K, then you use ML or machine learning to upscale that content. So I think you can see that there are tons of 8K TVs out there, I think for less than $1,000, at least in the US. So this is a question for Deepak at Roviero. Can you provide your thoughts on how your specific product can offer a solution for super resolution?
Sure, absolutely, yeah. And I think it's pretty interesting to see. Just before we go into the super resolution, just in this tech talk on Roviero, we looked at the application for inference first, and then at the Embedded Vision conference, we demonstrated along with people inference, the 5 camera, we demonstrated people detection, right? And here we are talking about super resolution. So just in this tech talk, right, we are talking about gamut of 3 different applications that this IP can solve. So I think absolutely correct. I mean, it's a little bit different topic, and before I dive into what solutions we have, let's talk about the problems that you face when you are doing the super resolution. And I think Parag, your example of TV is a great example, right? And along with that, what we are seeing is requirement in the cell phone space. Huge market, obviously, right? Where when you take a picture, you want to improve the quality of the picture, right? I mean, no matter, we've been seeing cameras, 4 cameras, 5 cameras. I don't know, at some point in time, the whole of the back of the camera of the cell phone will be loaded with the cameras, but to get more, there is no limit to amount of resolution that you can get on these cell phones, right? So the problem statement is, if I give you a simple example, is that just an HD image, right? You're looking at a 6 megabyte at 8 bits resolution, right? These are typically 14-bit resolution. When you go to 4K, it becomes 24 megabytes, and 8K is 100 megabytes, right? And there is no way. So the problem statement really is you can't store and process the data. If you got a 6 megabyte frame, you cannot say, oh, I'm going to take in all the 6 megabytes, process it, and then generate a 24 megabytes or 100 megabyte image for you. And then, so that's not a video, right? That will not, you get one flicker and people turn the TV off. So just on the lighter side, right? So the challenge really is that it needs to be processed in a streaming model as an online. So as the data is coming off of the sensor, right? Before even you have received the whole image, you need to upsample part of the image, right? And then take the next part in as in rows, and it's like a raster system. So that's challenge number 1, and keep your memory footprint small. Interestingly, at least right now, some of the models that we are seeing, they're not very large. These are encoder decoder based models. of the order of 20 to even 25 kilobytes, right? The models are not the problem. It's the amount of data that comes in and leaves the IP. And the challenge, especially when it comes to cell phones, is you can't have large IP in there. You cannot be storing large amount of, you cannot have a lot of memory in the system. So that's why, the challenge, that's the second challenge, is how do you meet the power, performance, and then area aspect of it. You're looking at generating this, if you're generating 8K image, 100 megabytes at 30 FPS, right? You're already looking at 3 gigabytes of data per second you're generating, processing in the IP, and you cannot be consuming that GPU type power. So that's where our solution comes in, and some of the customers that have looked at it is the GPUs. Using the GPUs, they were consuming power of the order of 20 watts to do something like that. And when we use an IP, embedded IP with the ARM processors in it, your power can go down to 2 watts. And you're looking at more than 10x reduction in power consumption and still be a fully programmable solution. So that's that's the part of it. But the challenge really, like I said, is being able to process all this large amount of data, get this large amount of input data in a streaming mode, run your IP, run your ML models on it, and keep on generating this data at the output. So there is no such thing as start and end. It's a continuous process that just keeps on going when the application is started. Yeah, so I think just in a nutshell, there's, as you can imagine, this is a myriad of problems or good news for the solutions there, right? That are related to the super resolution and sort of related to denoising as well. The same sort of concepts apply to denoise, where you can take a low resolution sensor and make it generate a much better image and do it in low light solutions. So like Roland talked about, some of the cameras that are security cameras, if you will, sitting in front of your house. We need to do that sort of amazing job at nighttime, right? When there's low light in there, and without having expensive sensors sitting in there. So that's when the AI comes in terms of denoising the image and then running AI models on it. Yeah, I think that's where we are. And happy to talk to anybody who wants to get in more details. Please do contact us.
Yeah, not only nighttime, raining, windy, all sorts of scenarios.
Snowing.
Absolutely.
Yes. Yeah, absolutely. Yeah. And I think Roland brought in some of the, some good use cases of it. Why not send it to the sensor? And we believe, I think the biggest use case is privacy, right? You don't want to send it to the sensor. Whatever is going on in your house in the security camera, right? So that's our biggest reason we tell, customers tell us why they want to implement all of these in-device compute.
Absolutely, totally agree with you. Yeah, and I mean there are laws against it as well. It's not like I think Europe GDPR is an example. So.
Yeah.
All right, perfect. So I think there's one question from the chat. Who wants to answer this? So the question is, which DNN architecture is used with a mix of 1 and 8-bit? As a backbone for detection? Example, DenseNet. Anyone can answer this question?
Let me try to answer that. I mean, I think it might be a little bit different answer for the question, but in general, I think the idea applies to all the networks. It really doesn't, from what we see is typically what you will see is these networks, they start out very wide in the sense that the data is large, the model size is small in the layers. And as you go deeper, the number of channels increase, the model size increases, but the data size becomes very small. So what that sort of intuitively will tell somebody is that when your model size is only let's say, in a particular layer, it's only, a few kilobytes, 1 or 2 kilobytes, right? There is no point trying to optimize that out to 1 bit. You're going to lose a lot of accuracy. Whereas later on in the network, when the model size becomes, let's say, even 100 kilobytes, it makes sense to optimize it out to from 8 bits down to 2 bits or 1 bit, right? So it pretty much applies to all the places, and the work being done here to get variable resolution, if you will, on the networks, right? It applies everywhere. It might not apply to super resolution or denoising, where your total model size is only 20 kilobytes, right? But when the model sizes are, hundreds of, or maybe even, tens of megabytes, then it makes sense to reduce the later on parts of the network. And that's where our IP can run a network with both, initial being 8 bits, then 4 bits and 2 bits of resolution in the network without loss to the accuracy. That's the critical part. Being able to run is one thing, loss to the accuracy is another.
Sure. Any comments from you, Roland? I know you also support BNNs and 1-bit, right?
Yeah, that's correct. But so we use our own model architectures. So both our own backbone and so both the encoder and decoder, our own architectures, and they're really tailored for people detection. And as I mentioned before, so all these layers of our stack, so data side, the model architectures and training strategies, the inference engines and IP core, they're all very much intertwined, which is allows to deeply optimize the whole solution. In this case, for people detection, we're planning to also use it for other tasks in the future. But we're really intertwining all those layers. That's how we get lots of optimizations and make our models both very accurate and extremely tiny.
Yeah, we follow kind of a similar approach. We've got our own custom model architecture for person, pet, vehicle, and now soon to be package as well. But we've also, for customers that bring their own, we've done, Yellow V5, we've done, other types of models as well. We're really not dependent necessarily on our own architecture. If the customer's got a already built out an application and is just looking to kind of run it through our tool chain to get it onto the Cortex A.
Got it. Thanks, Nick. All right, we have roughly 7-ish minutes to go. So I think it's a good point, a good time to kind of give final thoughts from each of them. I think maybe I'll start with Roland, because you have a hard stop in 5 minutes or so. So I think you've seen what we have gone through in this tech talk. From your point of view, how do you see this particular segment evolve from now till next 5-10 years from your point of view?
Yeah. I'm really curious, but I do have some ideas. So we ourselves, we keep making our people detection AI smaller and more accurate, but we're also planning to support more tasks, have more tasks in the pipeline: vehicle, pet, package detection, face detection, identification, things like that. Also, something that I'm excited about is gaze detection. So you can imagine in your home, if you're looking at the TV and you say turn on, the TV turns on. But if you look at the music installation, your music system, and you say turn on, the music turns on. Or if you look at your light switch, the light turns on. So I'm really looking forward to building solutions like that. So, and we were supporting more hardware platforms over time. So some specific accelerators, but also new ARM-based platforms. And something that I'm also very excited about is these battery-powered intelligent sensors. So battery-powered people detection cameras, for example. And this is what our technology enables, and it opens up sort of creates a whole new class of devices that currently don't exist yet.
Perfect. Thanks a lot, Roland. Yeah, I mean, I'm excited to see more battery-powered people detection, because you can just put them at different sites and just, draw analytics and then make use of those analytics to draw more, make future decisions, right? So I think that's what definitely. All right, so let's go to Nick. You have, Neutrino and your other Deeplite software. how do you see, from your point of view, how the market is going to evolve for you? ARM is continuously developing future Cortex-A, M, and Cortex-R cores as well. What do you see from your point of view, and how the market will look like?
Yeah, I mean, a lot of what we've been talking about today has been sort of commodity hardware or the low power. But the reality is, a lot of the new edge platforms that are coming out, they have NPUs and they have accelerators that are part of the board. So we're not ignoring that here at Deeplite. I mean, one of the things that when we talk about our model architecture optimization, for example, we're basically kind of a software accelerator for the hardware accelerators, and we've done some work even in collaboration with ARM on the Ethos U55, where we've seen detection models that get 70% faster after Deeplite and 60% less memory that's being used. And in some cases, like classification models, we've gone almost 500% faster. So the idea of leveraging our optimization capabilities in conjunction with these NPUs, we're actually collaborating with a couple of hardware accelerator companies that are coming up to market with new technology with our quantization capability, the ability to preserve accuracy while doing the slower precision quantization that their hardware supports. We're doing some pretty interesting things there. So that's kind of the way we're looking at sort of the next generation, is looking at the whole SoC, including the NPU and the CPU, and making the whole thing more efficient. But the Roland made the comment about battery operated. I think the future of this all is going to be about power savings, right? It's really going to be about cost per inference per watt. And there's all kinds of use cases, from electric vehicles down to battery powered doorbells, that need to preserve and do more with less in terms of power consumption. So I think a big part, I agree with Roland that the data is a huge area that we need to focus on. But the other end of the spectrum is being able to demonstrate that these capabilities are possible without having to recharge the batteries, every at a frequency that's reasonable.
Perfect. Thanks a lot, Nick. All right, so Deepak, up to you. How do you see the market evolve?
Yeah, I think from our perspective, like I said, it's very critical for Roviero and companies like us to really reduce the pain point for our customers, right? So part number one is making sure that they can very easily validate the solutions that we are providing, that they are building. That's part number one through our softwares and FPGA offering, right? And then the second part is to make sure that they are 100% confident that in future, once they build a silicon, they will be able to run their networks, right? So that's where the Corti-1 Premium comes in. And then the third and important part is the future networks, right? CNNs and RNNs, they are today, right? What we have built Corti-1 Premium for is for networks like transformers, where our customers should have confidence that once they build a silicon, 2 years down the line, we are not going to tell them, hey, you want transformers, here is the IP number 202, right?
Yeah.
And they should be able to run the same, on the same silicon, be able to run the transformer networks. And they're coming, right? Vision transformers are more efficient, they're more accurate, and we are making sure that on our current IP generation, you can run transformers and you can run any future activation functions that you might need. Even if a customer decides to do a floating point activation, sure, right? It's up to them. And we give them the freedom to write those activation functions as well. We don't have to write it for them. They don't have to expose those activation functions to us, because a lot of these networks are private and they don't want to expose it to us. So we give them that flexibility. So what I'm trying to come at is the future we look at is the more flexible it is, the better it is. And that's going to be a requirement for our customers, for them to be 100% sure that it's a fully flexible solution.
No, thanks a lot. So we are almost at the hour. I would like to thank Nick, Deepak, and Roland for their time. Thank you so much. And we do want to do more of these in the future related to machine learning and computer vision. And then we look forward to more detailed discussion. Thanks, everyone, and have a good rest of the day.
Thank you.
Thank you so much.